This is the very first video in the Kinetics chapter. We're going to start by talking about chemical reaction rates. And the different points in the outline for this section are revisiting thermodynamics versus kinetics. We'll talk about how to write rate expressions, and then we'll look at some data and look at how you can find the rate from a data set. Okay, so the first thing on the docket, we're revisiting thermodynamics versus kinetics. We looked at this a little bit in a previous video when we started the unit on kinetics. We said thermodynamics talks about how spontaneous something is, all about energy. The energy difference between the reactants and products predict whether a reaction will be spontaneous. And in kinetics, we talk about how fast a reaction happens, how much time it takes to do something. So we're going to be doing the kinetics half in this chapter, and this is your friendly announcement that just because something is spontaneous does not make it fast, and just because something is fast doesn't mean that it's energetically favorable. Remember that those are two different languages for talking about the same reaction. And just to make it super clear, here's a picture now that we know a little bit more about thermodynamics. So remember in the thermo chapter, we introduced a series of new variables: enthalpy, entropy, and Gibbs free energy. And we said these were path independent. Or it doesn't matter how you got there, just where you were going. The word we used for that was state function. So we said it didn't matter how you got there, only where you were going, because it was a state function. And we drew a picture that looked like this. We put energy here, and this axis is just reaction progress. And we learned about the reactant and product energy. So this is going to be my reactant or my initial energy. And this is going to be my product or my final energy. And we said it doesn't matter what path I take between these, the difference is always the same. So we drew the difference here as delta H total as the quickest way to get from point A to point B. But we also said we could go a different way. So we could go through some higher energy intermediate. So we could take one step, delta H1, up to this higher energy, and then take a second step, delta H2, down to the product. And as long as we start and end in the same spot, that should be just fine. Or we could even do another one. We could even go down to a lower energy state. We could start from the reactants and take our first step as an exothermic step. We'll call that delta HA. And then we can go from that low energy compound to the product, and a second step, delta HB. So the red and the green and the black are all different paths to get from the reactants to the products. And we said, in terms of energy, the total change in enthalpy is the same whether you do it in one step, whether you do it according to the green path, or whether you do it according to the red path. Those are all going to give you the same value for delta H because, oops, these were state functions. Okay, so that was all thermodynamics review. Now we're going to move on to the kinetics chapter, where it actually does matter what the path looks like. So in this chapter, we will talk about the rate and something called the rate constant. Those are the variables we use in this chapter. And those variables are going to be path dependent. So that means it does matter how you get from point A to point B. It is going to make a difference. So let's put our energies on the graph in the same spot as the last one. So here's my reactant energy. And we put the product energy here. And there's our delta H total. So the delta H doesn't matter how we get there, but when kinetics, we're going to start drawing energy curves that represent what happens in this middle area, reflecting that the path could be different depending on how we do the reaction. So we could draw a path that looked like this, or we could draw a path that looked like this, multiple bumps in it. We'll call that one number 2. Or we could draw a path that looks like this. And we'll call that one number 1. So in this case, the path does matter. So the different ways that we get there are going to give us a different rate. So the rate of path number 1 is not going to be equal to the rate of path number 2, and that's not going to be equal to the rate of path number 3. The amount of time it takes to get there is going to be different, and that's because of this barrier here, this height. The rates are different because there are different sized energy barriers. It makes the reaction take more or less time. We'll talk about this kind of a picture called a reaction diagram a little bit more in a future video. I just wanted to introduce it here as a way to differentiate between thermodynamics and kinetics. So now let's move on and talk about kinetics and what a rate expression looks like. Okay, so kinetics, we care about rate. We care about how fast things happen. And as you know, a rate is an expression of how much some variable is changing per unit time. And so in chemistry, we can write the rate of reaction, and the thing that it's going to be changing is the concentration of something in solution. So the change in concentration over time is going to be our rate. And we don't want to write that definition out the whole time, so we can turn that definition into math. The change in concentration, remember concentration we can write using brackets. Over means divide, and the change in time, delta T. So the shorter way to write it is the rate equals the change in concentration over the change in time. So let's talk about how the rate changes, because the rate changes differently depending on the conditions, depending on the reaction, and depending on which element or compound you're talking about. So here's a reaction. We'll use the decomposition of hydrogen peroxide into water and oxygen. Now let's think about what the rate is going to look like for each of these different things. So H2O2, that's going to be a reactant on the left side. And then what happens to the reactant? The reactant gets used up. It gets pushed, it goes away as we push towards the product side. So we're going to say it decomposes. And if something decomposes or goes away, its change in concentration is going to be negative. There's going to be less of it left after a certain amount of time than there was earlier in time. So the rate for these reactants, the rate of decomposition, those are going to be negative numbers. Decomposition rate is going to be negative. And then we can look at our products and we can see that the opposite is going to be happening to them. So our products are water and oxygen. And because they're products, they are being formed in this reaction. And when something is being formed, its change in concentration is going to be positive. You're going to end up with more of it at a later time than you did at an earlier time. So these rates are going to be greater than 0. They're going to be positive numbers. So rates of formation are positive, rates of decomposition are negative. And now we can write something called a relative rate to relate the rates of each of these different parts of the reaction together. So we can look at how fast this decomposition of H2O2 happens compared to the formation of each of these two. And they are related by the stoichiometry of the reaction. So that's why it's always important to balance your equation before you do anything, because stoichiometry is important. Okay, so let me show you what I mean. So I want to look at the rate of change of hydrogen peroxide. So delta concentration over delta time. And I want to compare that to the rate of formation for water and the rate of formation for oxygen. And they're related by the stoichiometric numbers. And I can tell just by eyeballing it, by looking at this equation, there's a 2 in front of the peroxide. So 2 times as much of this is going to be used up as oxygen, because there's only a 1 in front of the oxygen. And both of these numbers have a 2, so they're going to be used up and formed at the same rate. So what we do is we can relate these different rates by using 1 over the stoichiometric number in front of each. So we'll do 1 over 2 in front of the peroxide, 1 over 2 in front of the water, and 1 over 1 in front of the oxygen. And then we need one more thing. We need to add a sign to indicate which ones are being decomposed and which ones are formed. So the H2O2 is being decomposed, so that one gets a negative sign. Water and oxygen are being formed. And now we can set these relative rates equal to each other. So you can read this as peroxide is decomposed twice as fast as oxygen is being formed, or water is being formed twice as fast as oxygen is being formed. In the next video, we will look at a data set, and I'll talk about how to find the rate from a set of concentration versus time data.